Section 1.3 of the guided notes, finding the inverses of functions, and an inverse relation reverses the pairing of a relation. If a relation pairs with an input x with an output y, then the inverse relation pairs an input y with an output x. And this is going to make sense in a moment. The inverse of a function may or may not be another function. If the inverse of a function f of x is also a function, it is called an inverse function. And is written f to the negative 1 power of x. But that you read that as the inverse of x. So before we get much further along in this discussion of inverses, you've actually been working on inverses probably since about the 2nd or 3rd grade. And not with functions though, and I just want to call to your attention, there's a concept called the multiplicative inverse and the additive inverse. So a multiplicative inverse, right? If I have in multiplication, if I have 6 and I multiply it by 1 over 6, I get 1. And I can do this with any number. If I have negative 4 and I multiply it by a negative 1/4, I also have 1. If I have 999,000 and multiply it by 1 over 999,000, all 1. So they say 1 is a there's a multiplicative inverse in multiplication, and your inverse is you're basically trying to return 6 times some number to make 1/6, or to make 1. Now addition has the same concept with inverses, and hopefully this little sidebar doesn't get you too confused. But if I have 5 and I add a negative 5 to it, I get 0. If I have 400 and I add a negative 400, I get 0. So in multiplication, right, the inverse of 6 would be 1/6. In addition, the inverse of 5 would be negative 5, and so on. Now, functions also have inverses. So, in a sense, what that means is, if I put in, for example, in this chart below, a negative 4, I'm going to get a negative 2. But if I put a negative 2 in to the inverse of that function, I'm going to get 4. So in a similar respect, right, if I multiply 6 by 1/6, I get 1. And if I multiply 1/6 by 6, I get 1. So it kind of works forwards and backwards, if that makes sense, when it comes to inverses. And that's basically the fundamental concept behind inverse functions, is one function's domain will be the inverse's range, and vice versa. So, and it says as much in this preceding examples. Below is the domain and range of the function. Notice how its inverse switches the numbers in the domain and range. In this example, the inverse of the function was also a function. And what that means, right? This is actually review from last year. That section where people were, I'd ask, is it a function or is it not a function, and how do you know? We actually did that for a couple weeks last year. And the easy way to answer that question was, does every input value does every input value in the domain have only one output value? And hopefully you're getting adjusted to reading Mintonese, output value in the range. And in this case, it's true. Now I'm going to fill in these numbers here. Right? If one's domain has -4, it gives me an output of -2. If I put a -2 for the inverse, I'm going to get -4. And if it doesn't work out that way, then you don't have the inverse. So moving on to the next section, the guided notes. Right, and this was additive inverses up here, just an example. So in this example, the function has an inverse, but the function's inverse is not a function. And the reason that is because you can't have one input going to two outputs. That violates the rule of being a function. It works on this part, right? One input can have the same output, but one input cannot have different outputs, right? These are different. These are different for the two. These are the same for the two. So, because the input values have more than one output value. And this right here, this whole thing right here, not a function. It would be an inverse relation, maybe. So now that we've established that not every function has an inverse, that's important to know. Let's talk about, well, how do I even make an inverse of a function? And we're going to start off with lines. Right? How do I make inverse of a linear function? So you're in luck. Every single linear function also has an inverse. So to find how to do that, we're going to take an example. And our example here is f of x is equal to 3x plus 4. But we're going to go through the steps first. So step 1, first thing we have to do, say you've got this formula here. F of x is equal to mx plus b. I'm not going to rewrite it. Let's see here. First step is substitute y for f of x. So instead of f of x equals mx plus b, you're going to have y equals mx plus b. Next step, solve for x in terms of y. Solve for x in terms of y. So I'm gonna divide up our work here. This went with step 1. Now solve for x in terms of y. So I'm gonna have to subtract b from both sides and divide by m, right? So x is going to be equal to y minus b divided by m. So this was step 1. Here's step 2. And let's see, step 3, switch x and y. Here's step 3. Y is equal to m minus b. I messed that up. Not m. X minus b. right? I'm just switching. For x, I'm switching y. For y, putting in x. X minus b over m. And then the last step, and this looks complicated more so at the moment because we're using all letters. But hopefully in a moment you'll see that it will make more sense. And then replace y with f negative 1 of x. So step 4, so step 2, step 1, step 4. And there you go. That would be the 4-step process to make an inverse of a linear function. Now let's try an example with actual numbers in it. So here we go. As promised, this is going to be a lot less harder than it looked. I'm going to replace f of x with y. So y is equal to 3x plus 4. And then I'm going to solve for x in terms of y. So I'm going to have to subtract 4 from both sides, and then I'm going to have to divide by 3. So I'm going to get basically y minus 4 divided by 3 is equal to x. Oh, and let me see, I should have wrote this out. Basically subtract 4 from both sides, and then divide by 3, and you get this. So after all of this, you will have y minus 4 divided by 3 is equal to x. Now we have to switch x and y, step 3. So x minus 4 divided by 3 is equal to y. And then last step, replace the y with an f negative 1 to the x to signify that this is the inverse. And then x minus 4 divided by 3. So there we go. And now we're going to do some comparison. This was the original function, right? Here's the original. This is the inverse. And let's take a look at their respective domains and ranges. So check it out. If I put in, right, these are all the x values, these are the y values, here's the x values, here's the y values. If I put in 0, 3 times 0 plus 4, what does that equal to? That's equal to 4, right? So let's just try some other numbers. What about 1? If I put 1 in for x, what do I have? 3 times 1 plus 4 is 7. How about 2? 3 times 2 is 6 plus 4, I get 10. And what about 3? 3 times 3 is 9, plus 4 is 13. Let's try 4. 3 times 4 is 12, plus 4 is 16. So if I did this correctly, my inverse should basically flip these around. And let's see if that is what happens. So if I put in for x 4 minus 4 divided by 3, right? That's going to be 0 divided by 3. What does that equal to? 0. So what about 1? Now actually, I shouldn't try 1. I should try 7, right? Try 7. Why 7? Well, I just told you the domain and range are going to flip. So what is 7 minus 4 divided by 3. It should equal 1 if this is in fact an inverse, and it does. All right. 3, you get 3 over 3, and 3 over 3 is 1. Now let's keep going. What about 10 minus 4 divided by 3? It's going to be 6 over 3, should be 2. Yep. So when I try 10, I get 2. What happens when I try 13? 13 minus 4 divided by 3 is 9 over 3. Do you get 3? You sure do. And as you can tell, right, it does wind up where the domain and range flip. So I just wanted to illustrate how, one's domain is the other's range, and one's range is the other's domain. So let's take a look at one more example and see if we can figure out the inverse of this function. Now it actually gives us the function for this graph. So let's just take a look at the original. We're going to call this one up here the original. And we're not going to worry about making its inverse right now. Let's just get some points plotted on our table and also on the graph. So let's see, here's water in thousands of gallons and time draining. So the swimming pool contains 600,000 gallons of water, and the amount of water in thousands of gallons remaining in the pool at the time t hours after the draining begins. So let's see. Well, how many gallons of water are there at 0t after no time? That'd be 600 minus 20 times 0, so that'd be 600. And what about what would I need to get to 0 water? How much time would that be? Well, if I plug in 0 for W, I'm going to get 0 is equal to 600 minus 20t. And right, I can add 20t to both sides. Hopefully your algebra game is strong. Is equal to 600, and then what's 600 divided by 20? To divide both sides by 20, you're going to get 30. So now that I have a value for at 0, right? Hopefully you can get the semblance of the graph. Maybe we should find, I don't know, one more point. So what happens when time is, you could maybe do 20 and 10. So you're just going to plug in for t. 20 times 20 is 400. 600 minus 400 would be 200. So at 20 minutes, it should be here. And 20 times 10 is 200. 600 minus 200 is 400. So at 10 minutes, it should be here. And there you go. There's your graph. So we haven't made our inverse yet. We've just got basically our original function. So now if we follow our steps to make the inverse, what are we going to do here? W equals 600 minus 20t. So I think what we should do here is solve for t in terms of w. So right now I have in terms of w. I actually need it in terms of t. So let's solve in terms of t. So I have to do the opposite of plus 600. That's minus 600. I've got w minus 600 is equal to minus 20t. And then divided by a minus 20. And what you're going to get, basically t is equal to w minus 600 divided by minus 20. And I'm going to try to simplify that. T is equal to negative 1 over 20 w, and then minus 600 divided by minus 20 is plus 30. So there you go. Now that's the there's one step. We have to switch now. We have to switch t and w. So the inverse of this would be w is equal to negative 1/20th t plus 30. So now that we've got the inverse done, right, here is, that's the original, this is the inverse. And if we're correct, basically this is the domain, this is the range. The range should become the domain, and the domain should become the range. So what happens when w is 0? Let's find out. 0 is equal to negative 1 over 20 t plus 30. So I'm going to subtract 30 from both sides. You're going to get negative 30. And I might have lost some of you after all this work here, but hopefully those of you that are still with me follow along. It's times by negative 120. I have to divide it by negative 120, and that's going to wind up where t is equal to 600. So it is in fact true, and it does work out. Now, what I really wanted to point out is, again, this is what happens if you did the inverse correctly. You can verify stuff that using the domain and range, that you've done the inverse correctly. So basically, I'm gonna fill in the rest of these points. We know the first one worked. We can try another one, right? If w was 30 equal to negative, and I'm using the inverse. Right, subtract 30 from both sides. You're going to get 0 is equal to negative 1 over 20t, which makes t, of course, 0. So everything's going to flip around. And hopefully you'll also recognize one thing, that the graph would be slightly different as well. The graph of the inverse would actually flip around like this. Here would be water. Actually, that wouldn't be the case. It would still be here and here, just the numbers would be a lot different. Right? If we still had w and t here, now we're talking about starting basically at 0 and 600. 30, 20, 10, something like that. So just a slightly different graph, different values. If you actually drew these two graphs simultaneously, be kind of interesting, some of the results you would get. But in any event, you've seen now the domain and range switch on this problem as well, and we figured out its inverse.